today. Cofunction is the first one. You can see there's 6 of them here. And again, as I mentioned, the Pythagorean quotient and reciprocal IDs that we reviewed yesterday, that we had learned last semester, those need to be memorized. Those will not be on a formula chart. Okay, but when we test next week, these new identities that we're learning this week will be on a formula chart. So you don't have to have them memorized, but you need to know how to use them, how to make the substitutions when appropriate. All right, so cofunction, it's easy to remember which ones go with each other because they're literally the ones that have co. So sine and cosine, tangent and cotangent, secant and cosecant. Those are your matches or your pairs for cofunction identities. Now, what their relationship is, what this comes from, you see pi halves in all of these. That's 90 degrees, right? In degrees, pi halves radians is the same as 90 degrees. So if you think back, my pen, to your basic right triangle trig, let's say this angle is theta. And let's say this is a 3, 4, 5 triangle, just for ease. So if I wanted to know sine of theta in this example here, what would sine of theta be? Three over 5, opposite over hypotenuse, right? Okay. They're telling me that's going to be the same. It's going to be equivalent to cosine of pi halves minus theta, or 90 minus theta. Okay, so this other acute angle, I'm going to call it beta for the sake of these notes. So beta and theta have what kind of relationship in this right triangle? We know the 3 angles have to add to what? And if that's a 90-degree angle, what do these 2 have to add to? So they're complementary, aren't they? So these 2 acute angles are complementary. So from theta, 3 over 5 is sine. But from beta, 3 over 5 is what? Cosine, because from beta, that's the adjacent side. So this is what this relationship is, where it stems from, where it comes from, is that these 2 angles, when you have complementary acute angles of a right triangle here, sine from one of the angles is the same as cosine from the other angle. Okay, so that's just how they are notating that these are the complementary angles. Theta, pi halves minus theta means the complementary angle. Does that make sense? So because you're just taking pi halves, or 90, minus whatever theta is, this ends up being the complementary angle to that. Okay, so that's the relationship here for those. The next one, we've got a little review, synopsis, explanation before we jump into what the identity is. This goes back to algebra 2, I guess, when you first talked about odd and even functions. We learned, and we reviewed it in Unit 1 this year, when we were talking about key features of functions. Do y'all remember the difference between an odd and an even function? Graphically or algebraically? Close. It does have to do with symmetry, but you've got it mixed up. Even is symmetric over the y-axis. It's over around the origin. It's the one that was the rotational, the 180-degree rotation symmetry. So yes, very close. You're on the right track. So a quick refresher. We initially learned them with like a quadratic. We said this was even because it was symmetric about the y-axis. Do y'all remember that now that I say it? You can fold it over the y-axis and everything matches up, so it's an even function. That's how you graphically would tell if it was even or odd. Odd was the cubic function. Remember, the cubic function was odd. It's not symmetric about the y or the x. It's symmetric about the origin, meaning you can rotate it 180 degrees and it looks exactly the same. Algebraically, that was the graphical test. The algebraic test is here. It said it's inputting a negative x and getting your output exactly the same as the original function means it's even. If you input a negative x and your output is the opposite of the original function, that's odd. So even was this odd. That's the algebraic test and what it looks like. Now, I'm not saying it's only the cubic and the quadratic. Those are just examples that we used when we initially learned that. But it's symmetric about the y or symmetric about the origin. Okay, now, thinking of it in terms of trig functions, you can think of it graphically. If I get a visual of the sine curve, that's the one sine cycle, right? But doesn't it repeats over here, doesn't it? So sine, that's one that's not symmetric about the y-axis, is it? If I fold it on the y-axis, it doesn't match up. But if I rotate it 180 degrees, is it symmetric? If I rotated this 180 degrees, would it look exactly the same? Yes, it would. So that means this is an odd function. Cosine, if you visualize it, cosine starts a cycle, starts high, ends high. Same thing in the negative side, right? So this one is symmetric about the y-axis, isn't it? So cosine is even. Okay, so if you prefer to think of things graphically, visualize the graph and it will help you remember if it's even or odd. As long as you remember that y-axis symmetry is even and origin symmetry. Oh, I just did that the wrong color. Hang on. I did even in pink a second ago. Let me fix that. Okay, or if you're not that visual, need the graph person, just think of the unit circle or any point on any circle. It doesn't have to be the unit circle. But if I have a point here, x, y, okay, this angle is alpha. That's the reference angle there. Okay. And then if I reflect that down here in quadrant 4, the x doesn't change, does it? Still a positive? But the y changes to negative. So if I have a positive alpha versus a negative alpha as my angle, as my input, it has no effect on the x value. But it changes the y to the opposite. That's what this is explaining here. They're saying if I input alpha, I get sine of alpha is y, because sine is the y, cosine is the x, right? So sine of alpha is y, sine of negative alpha is negative y. So that's this rule. You input a negative and you got the opposite function. But for cosine, if I input alpha, cosine is x. If I input negative alpha, cosine is still x. It didn't change. It came out exactly the same as the original. Right? That's the algebraic test for an even function versus an odd function. Yeah. All right. So that's just to help you understand why these identities, where they come from, why these are true. So cosine is the only even out of sine, cosine, and tangent. Its reciprocal is as well. The reciprocals are the same as their function that they are reciprocals of. So since cosine is even, that means if I input negative theta, I still just get cosine of theta. So I can just drop the negative. Okay, but sine is odd, as is tangent, which means their reciprocals, cosecant and cotangent, are odd as well. That means if there's a negative input, we can bring that negative and put it outside the function. So far, so good? So let's do a couple of examples mixing these two new identities and the ones that we know already, Pythagorean, reciprocal, and quotient, plus our algebra skills. All right, in example 1, it wants us to simplify by writing as sine and cosine. Now, before I jump into writing this as sine and cosine, though, I'm first, different colors that I've been using. That stands out to me because there's a negative input. So I'm going to look at my odd and even functions and ask myself, okay, is secant odd or even? It really doesn't matter if you know what it's called, but you'll be able to look at this and say, oh, well, secant of negative theta, that's the same thing as secant of theta. So it's going to make my life easier to rewrite that just as secant of theta and get rid of the negative. Now that I've gotten rid of that extraneous negative that would have been kind of confusing, now I'm going to replace everything and put them in terms of sine and cosine. So cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent, that's the quotient identity cosine over sine. All right, so I've got these two fractions multiplied. I can just write as 1 over sine cosine. Now I'm trying to simplify this down. This isn't very simple yet, so I'm going to try and keep going. Okay, what's different about simplify and verify is that with simplify, you don't have an equal sign with what you're trying to work toward. So I actually think simplify is a little harder. Verify, you know what you're trying to end up with. Okay, so simplify, we're doing the same thing as verify, except we don't know what the end game is. We don't know what we're going to end up with, but we know we're trying to condense it down and simplify it to something less complicated. Okay, so if I want to try and combine this to a single term, I have to be able to subtract the fractions. What do I have to have? Okay, so what can I do to get a common denominator here? Good. McKenna, this pass came for you and it says to go now. You can come grab this to Ms. Lopez Bauer. All right, so once I get a common denominator, what's that going to mean my numerator is? What's it become? 1 minus cosine squared. Let me write that way. And my new common denominator Now, does something stand out to you yet? I cannot cancel because in the denominator, cosine is a factor, but in the numerator, there's a minus sign here. Remember, y'all can't cancel across, like if there's a plus or a minus, only if they're factors being multiplied. Yeah, I can use Pythagorean identity. That right there, 1 minus cosine squared is the same thing as what? Sine squared. I'm running out of space, so I'm going to have to go to the right over here. Then what's going to happen? Now I can reduce the sign in the denominator with one of the signs in the numerator. So now I'm left with sine over cosine, which is tangent. So that's pretty simple, a single trig function, right? So I simplified that cosecant theta times secant of negative theta minus cotangent of theta all the way down to just tangent of theta using algebra and identities. I didn't highlight here. This is the reciprocal I used here and here. And this is a quotient I used here and here. The rest, oh, the Pythagorean. Let me highlight the other half of the Pythagorean there. Good? Okay, let's try 2. So I've got 2 fractions that I need to combine because it says simplify by combining fractions. And what did y'all just tell me that I had to have to combine the fractions over here? So I need a common denominator here as well. On this one, I was able to just multiply one of the fractions to change the denominators to match. Can I do that here? So what do I have to do if I can't change just one of them? I have to multiply them by each other, right? I'm gonna have to change both of them. So the fraction on the left is gonna have to get multiplied by cosine theta in both the numerator and denominator. And the fraction on the right is going to have to get multiplied by 1 plus sine theta in both the numerator and denominator. All right, so this is just algebra. I haven't done any trig yet. This is getting a common denominator. So this numerator over here will become cosine squared plus, and then over here, if I FOIL this out, first, outer, inner, last, I could do it that way, and I would have to multiply the other side by the conjugate of the denominator. So I know what you're thinking, and yes, but it would be a little more complicated doing it that way. Okay, so over here, if I FOIL out this numerator, I'm going to end up with a 1, a sine, so 2 sine, and then a sine squared. So 1 plus 2 sine theta plus sine squared theta. Are y'all okay with how I got my numerator? Okay. My new common denominator, I'm going to leave in this factored form. I'm not going to distribute that. Okay, can I do some simplifying in my numerator? You'll see anything that stands out to you in the numerator? Say it again. There's sine squared here, and there's a sine term here. Don't be afraid to guess. I would only be able to factor out the sign from these two terms, though, not of the whole numerator, because they don't all have sign. What if I rearranged this? What if instead of writing it 1 with the constant and then the sign squared, I wrote it in the form we're used to seeing quadratic form trinomials in, and have the sign squared first, and then the 2 sign, and then the 1. Does that help you see anything? Yeah. I have cosine squared plus sine squared. They didn't have to be next to each other to be able to do this. I could have just seen cosine squared and at the end was plus sine squared. Okay, but it's easier for y'all to see when they're next to each other. That's a 1. Okay, that's the trig identity. I'm just gonna replace it above it to save us some writing. So that's a 1. I'm just replacing that whole thing with a 1. Now what can I do in the numerator to simplify a little? Yeah, combine these like terms, huh? So I end up with 2 plus 2 sine theta for cosine times 1 plus sine. Anything else I can do in my numerator still? Factor out the 2. Very good. So if I factor out the 2, thank you. What does that leave me with? 1 plus sine theta. And that helps me out because that 1 plus sine theta is a factor in the denominator as well, isn't it? So now that can reduce. So now I've just got 2 over cosine theta. That's pretty simplified, but I could make it a little simpler by writing it not as a fraction. If I didn't want it to be a fraction, what could I do? I could, instead of having cosine in the denominator, I could write it as secant in the numerator as its reciprocal. Okay, I'm going to drop that off to the side for those who don't immediately see that. You can think of this as 1 over cosine times 2 if you needed to. That's the same thing, right? And then that is secant times 2. So let's see. I highlighted the Pythagorean identity, and then here I used reciprocal. I don't know if I used any other trig in this one. This was mostly all algebra. There's 2 trig IDs. All right, number 3. They want us to simplify by factoring. But before there's nothing to factor right now. It looks like both terms have a sign, but they're not of the same thing. This is sine of theta. It's actually sine squared of theta. And this is sine of pi halves minus theta. That's not the same, so I can't factor at this point. But I can replace this with what? Cosine of theta. That is our cofunction identity, right? So I make that substitution. The rest of this stays the same. Now, can I factor? Is there a GCF between these two terms? Cosine of theta. Both of them have cosine of theta. What am I left with if I factor that out? Sine squared minus 1. Any bells going off yet? It's what? Very close. Let's think about it. Here is the original Pythagorean identity, the way that it's written. There's lots of ways to move things around here. Yeah, because the sign is positive and the 1 is negative. That means the 1 was subtracted over here. The cosine had to have been subtracted to the other side. So this would be negative cosine squared. It's still part of the Pythagorean identity, but don't forget that negative. And then what am I going to end up with if I multiply cosine by negative cosine squared? Negative cosine cubed of theta. All right. The check for understandings I want y'all to try on the back correspond pretty well to these 3 on the front. And then the last one we were supposed to look at today, we're not going to finish, is sum and difference. So we'll finish that up tomorrow. But you can go ahead and take a look at it if you wanted to, but definitely try these 3 check for understandings for that front side and work on some of your ALEX. That 7-question ALEX assignment from yesterday is due tomorrow before midnight. So I would try and get some of that done, or some more of that done if you've already started. Okay, so then tomorrow we'll finish up talking about sum and difference, and we'll move on to the 3rd page as well.